Okay, so the talk is about probabilistic fair clustering, and this project was done with Brian, Leo, and John. Okay, clustering is a fundamental problem in operations research as well as machine learning. So, for example, in operations research, you have a collection of clients and and K-many facilities which you wish to place, and you're supposed to place them in such a way that you minimize the clustering cost. Okay. In machine learning, you basically have a data set and you wish to cluster in order to reveal some patterns, such as the four well-separated clusters in this example. Okay, so in this project, we'll be focusing on center-based clustering. Okay, our input consists of a set of points C. There's a distance between them. So for every I and j that belong to C, we have a distance d of I and j, which is a metric. So it's a metric, satisfies the properties of a metric, the triangle inequality, non-negativity, and the distance is equal to 0, only if we compare the point to itself. And we're also given a number of clusters K as part of the input. And the output should be a set of centers S, and the cardinality of S should not exceed K. And we're also supposed to come up with the assignment function, which assigns points to centers. And thereby, this is how the clusters are formed. So these are the clustering. Okay, so these are the clustering objectives which we will be concerned with. The K-center objective, which minimizes the maximum distance from a point to its center. The K-median objective, which minimizes the sum of the distances of a point away from its center. And the K-means, which minimizes the sum of the square of the distances from a point to its center. And all of these can actually be written in one form. So if we were to take the distance between a point and its center, we were to take these values and stack them up in a vector, such as this. So d1 phi 1 all the way to dn phi n. Then really this corresponds to the different norm we take of that vector. If we take the infinity norm, then we're talking about the k-center. The one norm is k-median, and the two norms k-means. Okay, so we just want to note that in the absence of constraints, there are no constraints on the clustering. We just minimize the clustering objective. The assignment function is trivial. You just assign a point to its closest center. So if we have these set of points, if we were to do clustering with k equal to 2, then we'll just end up with these clusters. The x is a center, and we form these two clusters. And that's easy to see that this would actually minimize the clustering cost. Now, if we have a constraint, so for example, we're given the same set of points, and now the constraint says that each cluster should contain at least 3 points. It's clear in this case that this cluster cannot maintain as it is because it only has 2 points. So what's going to end up happening is something like this, where we have this point actually assigned to it the center that's further away. It's assigned to the center that's further away to maintain, to satisfy the constraint. I'm just mentioning this because basically fair clustering is also an instance of constrained clustering, and we will see this behavior as well. So the assignment is not trivial in fair clustering. All right, so the definition of fairness, which we will focus on, is what they call demographic or group fairness. And demographic or group fairness is based on disparate impact, which basically says that we should get the same outcome for the different groups we have. So the first step in group fairness is basically given a collection of points, you'd have to assign their group memberships. And we do so by assigning them colors. So red denotes one group and blue denotes another group. And definition of group fair clustering, or we'll call it fair clustering from now on, is that each color should contain the right proportions, each cluster should contain the right proportions of each color. And usually right proportions means close to population level proportions. So in this example where we have red and blue points, they occur with the same number, right? So an equal number of blue and red points. So the fair clustering should have clusters that contain almost the same number of blue and red points. And this is basically what would happen. So if we use the color agnostic solution, we'd end up with clusters that all consist of the same color for this example. But if we were to use the group fair clustering, we would basically end up with clusters that mix the two colors and almost basically maintain a 50-50 proportion. All right, now, if we wanted to formalize it more, so basically for each color, we would have lower bounds, L blue and L red. We're just going to talk about two colors for simplicity. And the upper, we'll also have the upper bounds, U blue and U red. These are, of course, numbers between 0 and 1. We would have the same clustering cost as the k-median as an example. And we'd have these constraints. So CI, the cardinality of CI is just the number of points in cluster I. And CI blue is the number of blue points in cluster I. And similarly, CI red is the number of red points in cluster I. And what we're saying is that the constraint says that the number of blue points cluster I should be at most the total number of points cluster I times this proportion, upper proportion bound U blue. And of course, it should not go below the lower proportion bound times the total number of points in the cluster. And similarly, we have constraints for the red color as well. Now, an issue is that we may not have perfect knowledge of the group memberships, and this was, this is basically, it was indicated in the collection of papers. So memberships may not actually be available at all in the data set. In this case, we might use an ML model to predict the group memberships, but the ML model is not perfect and it fails with some probability. We might also have noise in the memberships due to error in filling the information, or because the group memberships could be released in a differentially private manner. So in this project, we assume that we have a complete probabilistic knowledge of the group memberships. So we basically say that given a point J, it's red with probability PJ red. It's also blue with probability PJ blue. And for this, the colors, we also know the probabilities. Okay, and we know the probabilities perfectly. Now, given this setting, we basically need to modify the definition of group fair clustering. And what we do is quite simple. We just say that you should maintain the proportions and expectation instead. So we have the same clustering cost, but this time, instead of maintaining the, the amount of blue is now the expected amount of blue in color and cluster I. So just to clarify what the expected amount of blue, you just sum, so the sum over J that belongs to CI, right? All of the points that belong to cluster CI, and you sum the probability of them being blue. That's basically what it means, okay? And you can see that this actually retrieves the definition of fair clustering when the group memberships are perfectly known, because the probabilities would just be 1 or 0, and would just, the expected value of CI blue would just be the number of blue points, okay? So let's just get a feeling. So basically, this is now a given problem in probabilistic fair clustering. So the top left cluster is, the shade basically indicates the probability of taking on that color. So this is, blue with probability almost 1. On the right, top right, we have red with probability almost 1. And you can see the bottom is like they take on this color with probability something like 0.6 or 0.7. So this is the original problem. What would fair clustering do? It would basically cluster in that way because it wants to maintain the color proportions and expectation, right? So it has to mix the things which are, a bit blue with a bit red, and, really red with really blue. Deterministic fair clustering, on the other hand, if it were to ignore the probability of being red or the probability of being blue, would give us something like this. All right, and clearly that's different. Okay, so now let's talk about our algorithms for probabilistic fair clustering. Now, the first thing is that fair clustering is NP hard, and the hardness of fair clustering follows from the hardness of the unconstrained version of clustering. So all of the clustering objectives, k-center, means, and median, they're all NP hard. So what we're looking for is an algorithm with some form of approximation ratio, not an algorithm that solves the problem exactly. We have the following theorem for the two-color case. It says for the two-color case and any clustering objective, if we have an alpha approximation algorithm for the ordinary problem, the problem that is fairness agnostic, then we can get an alpha plus 2 approximation ratio for the objective, okay? And when it comes to the fairness constraint, we have an additive violation of 1. So we don't actually satisfy the fairness constraint exactly, either we violate it by 1. And just to clarify what that means, so this is the fairness constraint, and you can see a -1 right there and a +1 right there. I just want to clarify that, +1 doesn't show up in the proportion bounds because that would basically lead to, trivial results. So if you have like 0.7, the upper proportion bound is 0.7. It's not going to be 1.7 because that would just be meaningless. That's basically 170%. All right.
So Marina and Laro, Marina and Syed, can I interrupt now with a question, or do you
sure,
want me to read? Yeah. This is a technical question because this kind of thing arises in some other settings. So are the inequalities perhaps strict in your additive violation of +1? They probably are strict, right? They're not less than or equal to, but less than.
I don't think they're strict.
You don't think they're strict. So actually the equal to is also possible.
No, it's actually just less than, not
less than. Okay.
Okay.
Sure. Yeah. So yeah, that can be helpful in some situations because, for instance, if if U blue times CI was not an integer, right? Then you recover. You actually don't lose anything, right? Because if U blue times CI was say 6.5, then you still get at most 7, which is what you'll get without any loss as well, right? Oh, no. This is the expected value. I see. Okay, I see. But still, yeah, my suspicion is you get strict inequality, and that's what you think is the case also.
Right.
Okay, very good. Thanks.
Okay, so, yeah, all right. So, as a reminder, we're just, again, what are we solving for? We're solving for the set of centers S and the assignment, which assigns points to centers, okay? So, our algorithm basically follows these 3 steps. And the first step, we basically run an ordinary clustering algorithm to find the collection of centers S. Then after we find the set of centers, we use an LP, and we use a linear program, that's LP stands for. And the LP basically will satisfy the fairness constraints, and will recover the assignment phi LP, which could be fractional, so we cannot use it. And that's where we use the rounding step to basically get an integer assignment phi. All right, so let's see how that
Syed, there's just real quick, there's a question in the chat.
Right. Oh, let me look at the chat then. Could you tell me what the question is?
Maybe I could just say it out loud. I was wondering, maybe I missed this on the earlier slide where this was introduced before the algorithm slide. I was wondering why we're looking at expectations instead of looking at the probability that the constraint is satisfied. Because I could imagine, for example, an algorithm that on average assigns like the good cluster, quote unquote, to the blue points with the red points. So its expectation is fine, but in reality, it always gives one group or the other a sort of unfairly good result.
Right. So that's actually a good point, right? So you could actually have this algorithm operate on an example where basically, it produces clusters which are fair in expectation, but in realization, it's basically either completely red or completely blue. Right? That's your question, and this could happen. So, well, I don't know how to. This is actually, a higher standard, and it should actually be satisfied. Now, if you were to assume that, for example, there's some sort of concentration around the expectation, then that would be fine, to satisfy an expectation, because, imagine like something like Gaussian distribution where you're centered around the expectation, all right? Then you would be fine.
So do you know about the concentration properties of your rounding algorithm?
So we have an algorithm that doesn't even involve concentration inequalities. I'm talking about this depends on the distribution, actually. On the input, I mean, not on the algorithm.
No, but what I mean is I think David's question is a good one, but I think in fairness to your work, it's also a hard problem because, probability is a nonlinear function while, the expectation is a linear function, right? So, but it may be that let's assume that the input is, by the way, Marina and Syed, let me know if you want to keep these questions to the end. So I didn't want to interrupt the flow of the talk. So if you folks would like us to defer these, we can do those. But my point is, even if the input point set was worst case, was adversarial, it could be that your rounding has some good concentration properties. That's also often challenging. And having worked on clustering for a while, I know that that's not a big problem, but I think it's a well-motivated question. Assume the input is worst case, but how much correlations and concentration can you introduce as part of your rounding in order to be able to say something about the probability of violation.
So I'm not sure I understand the question, because we do satisfy this constraint deterministically.
You do satisfy it, but David's question was, what if your constraint was, okay, so let's say U blue was 0.7, right? So on the upper bound side, you know that the expected number of blue points in any cluster is at most, the expected proportion is at most 0.7, right? The question is, what is the probability that it becomes more than 0.9? Can you bound those? That was David's question. Now the trivial bound is given by Markov's inequality, right? Markov's inequality would say that this probability is at most 0.7 over 0.9, which is something reasonable. But if your rounding algorithm has a lot of independence or negative correlation like properties, you'll be able to give much sharper bounds than Markov's inequality. I think I'm sort of maybe extrapolating beyond David's question, but my question is, so you may be able to get some stuff even if the input point set is adversarial, basically. That's what I'm saying. We can also handle this offline, but do you see what my question is?
Right, I get it. We haven't actually thought about that, yeah.
Sure, okay, yeah, and I think that's a hard problem, but it's very interesting, yeah.
All right.
Yeah, thanks, I'm done, yeah.
Okay, so, all right, so, okay, so let's talk about step one of the algorithm. So we have the collection of data points. In step one, we just simply run an alpha approximation for the unconstrained problem. So after we run step one, we might end up with a center right here, C1, another center, C2. All right, so now that basically we have the set of centers, we need to find the assignment function phi. All right, so this is actually a different problem than clustering, because you basically now know the centers. You just need to assign the points to the centers. So it's a good question to ask if the problem is actually still NP hard, now that the centers are known. And it turns out that the problem is actually still NP hard. All right, and the way what we do to solve the problem is to use an LP relaxation method. So this is basically our, first of all, integer program. We have the variable xij, which is a 0,1 decision variable. Xij is basically equal to 1 if point j is assigned to cluster I, and it's 0 if point j is not assigned to cluster I. All right. Here we have the objective, which is simply the clustering cost. And this constraint, we're simply saying that the sum of xij over all the centers over all I should equal 1. And this simply amounts to saying that the points should be assigned to a cluster. Right, and then here we have the color proportionality constraints for cluster for cluster 1, and we have the color proportionality constraints for cluster C2. Now we haven't really done anything. This is the integer program, so it's the same exact problem, just written in symbols, and this is also NP hard. The LP relaxation simply amounts to letting xij be between 0 and 1 instead of being either equal to 0 or 1, and this is basically now an linear program, and we can solve it to optimality in polynomial time. All right, so now we have the set of centers S, and we have xij, the optimal solution from the linear program. The problem is that the xij from the linear program could have fractional values. So for example, it could be like 0.2 and 0.8. And this is not something we can use, because the point has to be assigned to one cluster, right? So we need to round xij to integer values x bar ij. The rounding method we used is based on minimum cost max flow. So just a reminder of minimum cost max flow problems. We have a direct graph, we have a source, a sink, we have demands and capacities in the flows, and we have costs as well in the edges. Right, the nice property of minimum cost max flow problems is that if the parameters of the problem are integers, then we can get the optimal solution with integer values. And this is basically the property we use to get values for xij that are either 0 or 1. Clearly something, must go wrong, because we basically started with the integer program, right? We got the LP solution, and now we're rounding it. And, minimum cost max flow is going to get the optimal solution. That, we can't solve the problem exactly because it's NP hard. So what goes wrong is that the proportionality constraints end up being violated. Okay, so but the violation is bounded by 1. So I think we really have to pay attention to like three things. So A, B, and C. So A is the clustering cost. All right, so this is the LP solution. This is the clustering cost the LP solution gave us. This is the size of the cluster B. It appears here and there as well. And here is the basically the amount of, you know, blue that cluster one receives. Okay, so at a high level, the network flow diagram assigns for every point j, we basically have a vertex of supply 1. That's basically kind of like xij being equal to 1 or 0, right? And because the flow has to be an integer, this basically decides where it's going to be, which center it's going to be sent to. The distance d of I and j is encoded in the cost in the arc where the flow goes. And we basically set the demands for each center in such a way that what the center ends up receiving is either the floor of xi, the floor basically of the cluster size that came from the LP, or the ceiling, right? So this is basically roughly how we, you know, maintain A by encoding the distance and the cost, roughly how we maintain B. But you can see how the violation shows up because we have floor or ceiling. Now the question is, how do we maintain C basically, right? The amount of, basically amount of blue color. So for the two color case, we actually just need one probability value, right? Because the probability being red is just the complement of being blue. And, you know, we'll not go into detail, but at a high level, we basically sort the probability values. So this V1, V2 are sorted according to their probability values. And the constraints of the network flow diagram enable us to bound the additive violation. If you actually go through it, you'll end up with a telescoping sum. So you have P1 max minus P1 min, then here plus P1 min, they end up canceling out. And then you're just left with P1 max minus P min basically. And you know, the maximum value is 1, the minimum value is 0, and this is basically at most 1. Okay, so what about the multi-color case? So basically get similar guarantees, but under the assumption that the cluster size is large. So basically, what the idea behind the solution is that we do independent sampling. So if we assume that each cluster size is large, and if we sample, just to be clear, so independent sampling is that you go to each point has probabilities over the colors. You basically sample the point. So if it's PJ red, you do independent sampling, it becomes red with probability PJ red, and becomes blue with probability PJ blue, okay? Now, if you do independent sampling, then you can actually use the Chernoff bound, which would tell you that the deterministic assignment now you get from independent sampling will be concentrated around the expected value, okay? So basically, this is kind of the sketch of our solution for the multicolor case. Basically take the instance, we do independent sampling, we end up with a deterministic instance. We then run deterministic fair clustering, and we actually retrieve a clustering that's equal to the probabilistic fair clustering. All right, so let's talk about the experiments now. So all the data sets we use are from the UCI repository. We mostly use the k-means clustering. For a given color H, the lower and upper bounds are basically set to 1 minus delta and 1 plus delta times the population proportion of color H, all right? And can be seen that the smaller the value of delta, the tighter the proportionality constraints are, okay? And we use two measurements. One is the maximum additive violation and the price of fairness. The price of fairness is basically the cost of the fair solution divided by the cost of the color agnostic solution. And the price of fairness obviously has to be always greater than or equal to 1. So for the two color case, we have the bank data set. We use the whole data set, and that's around 4,500 points. The question is, how do we obtain the probabilistic assignments? Because, you know, all of the data set, the group memberships are there exactly. So what we do is that we perturb the memberships with some probability. So we can think of it as like the accuracy of a model predicting the membership, PACC. And here are comparisons to the unfair solution. So if you can look that, you can see that the additive violations of these are the additive violations. So the additive violations of the unfair solution are much larger than the additive violations of our solution, which really has an additive violation less than 1, theoretically and empirically. The price of fairness is also not that large. So the highest price of fairness we get is 1.01. Okay. All right, so here's a question. What is the effect of PACC on the price of fairness? So PACC, again, is like, imagine a model predicting the group membership. When PACC is equal to 1, we only have 2 colors. When PACC is equal to 1, then it knows the group membership exactly. When PACC is equal to 0.5, the lowest value, it's just making a random guess. So when it's equal to 0.5, the problem really doesn't have any color in it, because every point is equally likely to be red and blue. And this is where we end up with a price of fairness of 1. As we increase PACC, we see that the price of fairness actually goes up. All right. And we also notice larger values for the price of fairness when delta, the proportion bounds, are set to lower values. That is, the problem is more constraining. We see that the price of fairness is larger. Now, what happens if we use thresholding? So one idea is to, well, take every point and get rid of the probabilistic assignments, just assign each point the most probable color, and then just use deterministic fair clustering. What would happen? So we can, this is actually not always possible. So if you do this, you could end up with an infeasible instance. So if we were to consider all points are blue with probability P, which is equal to half plus epsilon, then if you were to assign the most probable color, then that would make the entire data set blue. Now, empirically, we can actually do this, but we do notice that the price of fairness is significantly larger. So the 2 lines here are actually the price of fairness at probabilistic fair clustering, which is close to 1. On the other hand, thresholding basically gets price of fairness that's almost 1.2. All right, for the multicolor case, we basically use the census data set. We subsample it to 100,000 data points. We have 7 groups in this data set. In this case, we obtain the probabilistic assignments by training an ML model on a subset of that data set and making predictions using that ML model. And again, we can see that our violations are quite small and that the price of fairness is reasonable. Although larger, we get price of fairness of around 20%, 30% actually. All right, that was it. So here are all the references.
All right. Thank you for the really great talk. So if anyone has any questions, you can unmute yourself now or post in the chat. Okay, David. Yeah.
I noticed that the sort of deterministic method where you assign every point its most probable thing did look like it did better in terms of additive violation than your algorithm. Did I read that right, or is it high?
Yeah, I think you read that right, actually.
Okay. I did have one question. I was wondering, like, it seems like this sort of pathological example may not always occur. So I was wondering if you had thoughts on how, like, what properties of the data set could use, like entropy or something, to see whether you can get some condition on whether this
right. So it's
deterministic
not
method.
pathological actually. So thresholding and then ending up with you mean this example, right? Where you because it's not so pathological. Because I actually ran experiments where I shrank that delta, tried smaller delta values, and ended up being infeasible actually.
Huh.
Okay. It doesn't actually have to be this pathological, by the way. All right.
Yeah.
Okay, well, I have a quick question. So I was just wondering about the motivations of like the model itself. So it seems like an oddly specific kind of definition to me, where you're saying that each point is assigned a color with a certain probability. Like, is that something that was just practically motivated, or can it be found in other places in like fairness literature or something like that?
Well, I think that's basically motivated in terms of what they call stochastic optimization, right? Where you basically have full probabilistic knowledge, right? So it does seem like the right place to start if you were to study imperfect knowledge of group memberships, right? And I'm not sure what else what was the question. Let me think again. So most of the work on imperfect knowledge of group memberships is like in supervised learning, and basically assumes, doesn't actually follow this setting where the probabilistic knowledge is actually fully known. But I think it's plausible, especially if we allow like perturbations in the probabilistic knowledge as well, right? So I have the probabilistic assignments, but then I say, oh, they're not completely perfect, right? So, you know, yeah, some deviation away from these probabilistic assignments is possible, and then you solve the problem. But, you know, this is basically kind of like the first step.
Okay, sounds good. Any other questions?
Syed, I'm not sure you touched upon this, but what about the, more than two color case?
All right, so basically we had that, that's basically where we do independent sampling, and we get the
Right.
deterministic instance, and we solve the deterministic instance, basically.
And you get the same violation bounds, the alpha +2 and the +1?
No, actually, not exactly. The violations become as proportions themselves.
Okay.
You get me? So basically, they're not additive violations.
Right. Okay. Okay. Interesting.
Yeah. So the guarantees are actually not as good. Yeah.
Okay. I had also messaged you. Do email me your paper and slides. Yeah, paper I know where it is, but slides, yeah, please send to me.
Sure. Sure.
Does anyone have any other questions?
I guess I was wondering also about extensions to the model. Like you mentioned one where, oh, maybe these probabilistic assignments aren't even good. I was wondering maybe about like maybe a case where you could say learn learn the actual assignments, like a sort of more dynamic model.
Right.
I was wondering if you knew about any work in that space.
No, I'm actually, well, there is some sort of work that's done in this space in supervised learning. So I think there has been some work which basically assumes that you can query more points, but you know it's a different setting. In supervised learning, you basically want to kind of maintain the same proportion on different groups, and they assume that you can query more points of a given group in order that your model accuracy, for example, is, you know, good on all groups. What we need, what I think is missing in this paper is really to talk about the fairness in terms of the realization, you know. So in realization, how fair would it be? Right, so that's one question. The second question is, for example, learning about the dependencies of the color assignments between different points, and that's when you can talk about the, you know, how fair the realization is. And yeah, yeah.
Cool. Thanks.
Any other questions? All right, well, sounds like there are no more questions. So yeah, thank you for the awesome talk. Yeah, I don't know if you plan on sticking around in case anyone wants to ask any questions in person, but yeah, so that's it.
All right.
Thanks, Ed.